We left off last time with the discussion of entropy, and we noted how both enthalpy and entropy can be combined in a way that we can make a more accurate, um, prediction of the spontaneity of a process. So we reviewed last time how the total change in entropy is what we're going to consider, and we're also going to factor in enthalpy as well this time. So our total entropy change we saw was the sum of both the change in entropy of the system and the surroundings. So say it was a particular reaction that we looked at with the delta S system, and then the solvent, whatever entropy change might have occurred in the surroundings. So when we look at our surroundings, the change in entropy of our surroundings, we can equate this to the enthalpy change of a system and the temperature in Kelvin that it's measured at, and the delta S of the surroundings, we can say that they are equal to the enthalpy change of the system divided by the temperature in Kelvin, but the inverse of that, right? So the opposite of that. So we put a negative up front. And using this knowledge, using this value, we can plug in to our total entropy change you see below here. So the negative enthalpy change of the system divided by T in Kelvin plus the entropy change of our system, right? So the enthalpy over delta T plus the entropy of the system gives us our delta S total. So we'll look at how Gibbs free energy, right, will be the sum, right, of enthalpy and entropy values. So let's look at the definition, right? Or the derivation, rather, of our delta G here. So we have our final equation that results, and this is what we're going to be most concerned with, right? So this Gibbs free energy is a factor of both the enthalpy term and we see over here the entropy term. So for our delta G, to give us a value that would be a spontaneous reaction, we would need to see a negative delta G. This you might have heard before. Again, in Gen Chem 2, you probably talked about negative delta G is a spontaneous reaction. And then a positive value for delta G will give us a non-spontaneous reaction. So let's look at a specific example here. So this reaction below is spontaneous. And we had discussed in section 6.2 how some molecules, and when they become more ordered, right, we go from 2 moles of things over here to just 1 mole of product, we would have a negative change in entropy. So that must mean that together, the enthalpy and the entropy term will give us a negative delta G, right? So this may be a negative change in entropy, which we know would not by itself give us a spontaneous reaction, but combined, we'll look at both the enthalpy value and then the entropy term. So if we had a greater magnitude for a negative delta H, that would kind of outweigh the positive value that we could have for our entropy term. So together, again, would be how we consider if we have a negative or positive Gibbs free energy. So if we do have a negative delta G, the process would be spontaneous, and we would call that exergonic. So it's similar to the term used for a negative enthalpy change, which is exothermic, but this is specific to all the values that we're including, both enthalpy and entropy terms, to give us our Gibbs. So this is an example of an exergonic reaction visualized in an energy diagram here. So we have our G, our Gibbs free energy plotted on the y-axis, and then we have our reaction coordinate, just like with our enthalpy free energy diagrams. For an endergonic process, you'll see a slightly different orientation. of our reactants to products. Let's go back quickly here. So we saw that our reactants were at a higher energy and our products were at lower overall energy. And that's reversed when we have an endergonic reaction. So energy, right, a positive delta G would be seen, and we have to add some energy to the system, and our reactants are at a lower energy than our products. So this is called an endergonic process. So we will end this section here, and we'll look at a continuation and relationships of delta G in our next section.